Thanks for coming down here, everybody. We're from Bloomberg. We got 4 guys here. We're going to be presenting what we do with JavaScript. We haven't really talked about anything we do publicly before, and we figured it would be a good idea just to kind of show the JavaScript community what we do every day at work, which involves a lot of JavaScript. So, thank you. So, as you see, homegrown server-side scripting. So what we do, as this implies, we do a lot of server-side scripting. So first off, about me, if you looked at the schedule, I am not Armin. I am Andrew Paprocki. Armin is right there. So I'm a programmer in R&D, been there for 8 years. I work on core infrastructure and making R&D productive, which is one of the key points here because that's where JavaScript has helped us a lot. So how many people here have heard of Bloomberg before? Okay, so is that how many people have heard of Bloomberg because of the TV station or the radio station? Oh, okay, that's good. So first employee is Mike Bloomberg. He's now the mayor of New York City. They wrote the first line of code in 1981. That was way before Windows even existed. The TV station didn't start until 1994. I say this because a lot of people they view our company as a media company and not as a software company. So we want to get across that we have a lot of code. When the TV station started, we'd been writing code for 13 years already. And as of right now, we have 30 years of code in our code base. That's a lot of code. And to let everybody know, we have thousands of programmers. A lot of people don't know that if you don't know anything about the financial world, but in our offices in New York, London, and even Tokyo, we have a lot of people, and making those people productive saves, equals real dollars to the company. So let's talk about code for a second. Code accumulates over time. The more programmers you have, the faster it accumulates. And this is especially true of compiled code. You wind up with tons of code. And what we found is that makes your company very, very slow. When I first started there about 8 years ago, the development cycle, it almost felt like a sweatshop because the work that people did there, like compiling all this code, going through this laborious cycle of testing things and rolling things out, it really made people not like their jobs, and it also took up a large amount of their time. So the other part of this is that not everybody can write clean compiled code. I mean, you guys see just even in the JavaScript world, what the difference is between good JavaScript and bad JavaScript. Now you extend that to C, C++, even Fortran, whatever, anything compiled, and you have all kinds of issues that you wouldn't even have in JavaScript, like memory corruption, memory leaks, things like that. And when you have 30 years of code accumulated, that stuff can be fatal to your company. So we discovered that JavaScript makes people productive. So about 5 years ago, we decided to use JavaScript to write all of our app UI glue. We, the infrastructure team, we build complex bindings that hook into all the legacy Bloomberg infrastructure. And for the most part, app development teams are focused on writing product, and they write JavaScript. That's like 1,000, 2,000 plus people writing server-side JavaScript every day. In order to make this realistic, you need a complete end-to-end solution. You can't depend on piecemeal things that kind of work together, or having a complex workflow that you have to teach to every new person coming in. You have to make every person productive from almost the moment they start. So what we wound up developing is, you can kind of think of it as like a grandfather to Node.js. Back in 2005, we made this switch, and we have everything that goes along with this to make people productive. We built our own desktop IDE. We have an entire deployment system with permissioning, handling rollout, backouts, exception handling, routing errors to the right people, debuggers, memory debuggers, code profilers. All of this stuff is built into our environment, and it all works around JS. So, like I said, in 2005, we started with SpiderMonkey. We decided to go with SpiderMonkey because at the time in 2005, that was really the only good option. And at the time, it was about SpiderMonkey 1.6, which, if you guys use SpiderMonkey at all, if anybody here works on server-side stuff, it's pretty old now. We decided to go with an object-based UI toolkit. To a lot of people, this will be familiar because it actually started out as GTK. It started out as like the general concept of GTK. Of course, it was completely carved out. The guts were taken out of it and replaced with all of the code that we needed in order to make it work in our client-server environment. But the idea remains the same. It's a GUI toolkit built around GObject. I doubt anybody, I mean, maybe some people in here have heard of Gob. You'll see an example of it later. Gob was a small project that somebody made on the internet. It isn't really used anymore, but it was something that we actually wanted. It was a way to write effective GObject code without all of the cruft and all of the, it's really tedious, like lots and lots of lines of C in order just to write a simple object. Gob kind of hides that all away, and it's a preprocessor that just generates the GObject code, and what you're left with is like basically a C#-like syntax. You declare classes, you have properties, signals, things like this, and when you use the preprocessor, it actually looks pretty nice. We had to implement our own equivalent GObject introspection layer. So when we took GObject was just GObject. The GNOME community didn't have any work in there related to introspecting these things or hooking it up to scripting languages. They were just starting to mess around with serious Python integration, stuff like that. GObject introspection was actually started the same year that we did this, but we essentially forked at that time. Even though we're built on top of GObject, everything has been all hacked now to work the way we want it to, so we're no longer really derived from that. We can't take any of their code anymore because it just doesn't apply to our code base. We had to implement our own equivalent of GJS, which is a fairly recent project, which came about at the same time that all of this server-side scripting stuff started to pick up. That project started in 2008, and again, we had this completed in 2005. So, to give you an example of what some of this stuff looks like, this is Gob syntax. If anybody here programs in C#, you'll see that this looks pretty similar as far as the outer class definition goes. Inside the curly braces is still C or C++, but we liked the idea of Gob, and so we took Gob and kind of made it our own. We used the open source one that exists for a little while, but it had a lot of things that were missing, so we decided to re-implement our own. So we had a guy that wrote our own in OCaml, and now it's a lot more complex. We have support for C# type attributes and lots of other nice language features that, again, just all pre-process into C code that's built around GObject. So this is what my group does. We write a lot of these objects. We have a core team that builds all of these things, and the app developers use all of this. So here's an example of this previous object. You wrap it, and because of the generic bindings, which are equivalent to GJS, it shows up in JavaScript like this. And you can see that the bindings can be pretty smart. Whatever logic you want to bake in there, you can. We want to catch errors before they occur. So if a native code object takes an integer and it gets something that can't fit inside of an integer, it's going to throw rather than trying to coerce it or clamp it or something like that. That's a general theme throughout all the bindings. You want it to throw as early as possible so app developers can fix whatever the problem is. So one of the problems is, so you create a server-side scripting environment. That's great. Now people can write JavaScript code, but JavaScript by itself on the server side obviously isn't that useful. You need to be able to do things with it. You need to be able to get data. You need to be able to affect whatever environment you're running in. So we at Bloomberg, over the 30 years that they've been in business, they've had a legacy data catalog that allows programmers to access almost every point of data that's available for every security in the known world. So you can take any unique security identifier, the example like a stock ticker, AAPL for Apple. And you can request one of like thousands of different data points if you need that in your app. You can say, I want the last price, I want the bid, I want the ask. You can ask about options stuff, about credit default swaps, about whatever. All of these things have unique codes, and you can request that data point. It's a couple lines of code, and it's not hard for people off the street to learn this. We built our own homegrown generic schema service architecture. App developers, the asterisk I had in there when I said app developers write JavaScript, they write that JavaScript for their GUI code, for their apps, but they're also responsible for any of these services that their app might talk to do more complex tasks. Because while JavaScript is great and server-side JavaScript is great, if you're doing heavy-duty computation, number crunching, things like that, you really don't want to do it in JavaScript. You want to farm it off to some native code that can do the right thing, maybe talk to different databases, different machines, and to the JavaScript, it just gets a response back with the data the app needs. We have our own in-house database that we've written because other database products, obviously we have those too. We have Oracle and SQL Server, basically DB2, every database known to man. But there was holes that needed to be filled for the really, really high-performing applications. Apps with really, really high read rates, where of course, you can build the same thing in any of these other databases, but the amount of hardware and the amount of money investment you would need in order to achieve the same read rate made this little niche for an in-house database. So for super high read rate, fixed record access, we have our own database, which is bound directly into the engine that people can access. So like I said, here's an example of, if I just sit down, I want to write an application and I want the last price of Apple because I want to stick it on my screen. This is an example of talking to our data catalog. It's very easy for people. You can give it any security that's available in our system. This PR005, that's the unique identifier I was mentioning about the security, the different data points. That just happens to be the data point for last price. You make a request and you get back both in string form and as a number if the data point is a number, because sometimes there's formatting and things like that are built in that would be in the string but not in the raw number. So everybody's probably seen XSD before. So assuming that somebody writes out an XSD, generates one of these services on our back end, builds it, deploys it, it's out there. Have a simple request response pair. This is bound also generically into our JavaScript. We have a generic catalog that's available from the engine. So I say, I want to talk to this service version 1.0, and immediately the objects I'm working with in JavaScript represent the XSD schema. And as you can see, the XSD schema, like the bindings take care of translating JSON into whatever the XSD schema is. So it's very, very simple for app devs to start using this stuff and get data into their application. Catalog is externally maintained. Everything is schema'd in version to manage rollout. Since it levels the playing field, now every developer in the company can look at the schema for anything and see what it is. You don't have to go hunting around for somebody's native code in like a different group that you've never talked to before. The services, because it's this generic framework, you externally configure them to run either in process or out of process. And also the transport is configurable. We obviously depend a lot on speed, so the majority of stuff in our system works via shared memory. That we try to use as little sockets and TCP as necessary, because everything passing around locally on the same machine with shared memory is a lot faster. But for compatibility, it also supports things like SOAP. So we have apps that are written in our homegrown server-side JavaScript that talk to services in external banks that are just Windows SOAP web services to get data directly into our server-side JavaScript. So it's very, very convenient. It all works through the same infrastructure. There's no difference to the app developer. There's always a but. Marshalling data to JavaScript sucks. Anybody that writes a server-side engine or deals with sticking data into JavaScript, you really, really don't want to work with large amounts of data in JavaScript, because everything you have, obviously, if you're pulling it from somewhere, it's already in the most efficient implementation possible if you've done that work. We want to have constraints. We like push onto our app developers a limited heap size. So you're running in this reusable container, your JavaScript app gets invoked. For all intents and purposes, you have a fixed heap. If you cross that heap boundary, your app is going to throw an exception. You're going to get an out-of-memory exception. And the way we enforce this is interesting, but it's separate from this talk. And speed is the final thing. The majority of our fastest applications run end-to-end from the time the user types it in to where the stuff is on the screen in like 18 milliseconds, 20 milliseconds, 30 milliseconds. We try to handle any event in under 100 milliseconds. So to us, speed is one of the greatest concerns because of data center usage, hardware usage, power consumption, things like this that you have to deal with when you have a large data center. So we have had to do a lot of optimizations that a lot of people haven't had to do. Like our environment has lots of caching built in, compiling things to bytecode, executing cached bytecode, anywhere where we can gain a couple milliseconds back, like we've tried to take it. The JavaScript, we ideally wanted it to just be rich glue. People can write complex apps with handlers, signals from GUI widgets, and access to data sources without having to stick all of the data into JavaScript. So here's a dumb, simple example of something. This is a real test screen just showing like some data in our GUI environment being shoved up onto the screen. It's all the members of the Dow Jones index in a list. This is the actual JavaScript code for that entire screen. This is a very simplistic example because there's no interaction with this UI. It's just grabbing a bunch of data and throwing it up onto the screen. But the key thing to take away from this is we've discovered through running all of our stuff that when you get data responses back, you want to try to deal with them with tools that prevent them from marshalling into JavaScript. So when we get back this data set of all the members in the index, we use this thing that we call a mapper to populate it into the grid. And the mapper just is predefined to say which fields in the series in the response get mapped to which columns in this grid, just using generic XPaths. Now, you know from here, design time. And what does it mean to write JavaScript design time? And it's just not editing JavaScript. We built a full IDE. This is all homegrown. We have support for debugging, profiling, all of this stuff in here, and this runs live in our environment. So at this point, I want to show you guys an example of how this stuff works. Of course, we have to resume it. This was set up before, but okay. Oh. Okay. So I threw this together before. This is just a dumb, simple example. People like pictures rather than words. This is just an image widget thrown on the screen, as well as a flag, which is just a specialized version of an image where a programmer could set a country code on it instead of having to remember some image resource. So just to kind of show you the interaction in here. So say I drag a button in here. Works exactly like an IDE that any other IDE you would expect, except as you can see, the code is JavaScript. Everything that's powering this screen is JavaScript. There's autocomplete in here. There's error checking. It tells you when you have syntax errors in your code, all this stuff. And this is hooked into our service layer and our database layer. So when you say application services create and you give it a service name, it populates the IntelliSense data with the stuff from the schema for that service. So it's very developer friendly for getting access to your data. And the other thing is that it's our environment tries to protect against errors. So here I'll show that you'll see that down in here, the image that I had dragged into that app is named image. And so I'm going to set the picture on that image to a string. Now, you'll see here that from the IDE, you're running this app live within our actual software that's sitting on client desktops. So there's no trickery here. It's running live, so everything you see is exactly what you're going to get when you publish this app. And you'll see when I click this, because I'm a developer, I get this nice little pop-up telling me that, oh, you did something evil. And I go and look in here, and it tells me integrated into the GUI that I got this JavaScript exception because I tried to assign a string that doesn't coerce to a number to something that expects a number. And you can see something that works in here. I'm going to set, so instead I want this handler to change the flag to a different country. You can see this is the workflow that we switched everybody to. Instead of compiling code, linking code, debugging native binaries, DBX, GDB, whatever, everybody programs like this now, and this increased productivity probably like an order of 5 orders of magnitude. I mean, it's like ridiculous how much more product comes out of the entire R&D of thousands of people because of this environment. And I'll show you what we do now. So say I want to take this app and I want to publish this app so that a client can run it. I'm on the phone with a guy in a bank right now and I want to demo something to him. So I like my app right now. I'm going to publish it. The other thing to note about this IDE is that there's no local files. This entire thing is inside of the cloud. Any R&D developer anywhere in the world can log into our terminal, access the development environment, and all of their work that they're editing and publishing, testing, it all goes into our backend. There's no local storage here. It makes it very convenient for people just to pick up work wherever they are and also work on laptops. So I've published this thing now. I had a version in here before, but I've published it. This is our deployment system. So right now, this thing is released to me on development. So I'm going to come shove this right to prod. I have super user access to do this, so nobody, it doesn't normally work this way. And I'm going to assign a mnemonic to it so that I could actually run this in our real software. And I'm going to call it JSCF. So this thing is now deployed. If I added a client to that list, if they come in here and just run JSCF, they get this application that I just wrote, which to show this to people, like to talk to them about a workflow that they want and then to prototype it during a lunch break and go back and show them exactly what they were just talking about an hour before is really powerful, and it's actually helped us win a lot of business. But I'll show you some of the tools that we built around this, because just building something isn't good enough. You need to be able to test it and debug it. So say I go back in here and I change it back to what I had before. This is going to throw an exception. I can set a breakpoint here. I could come in here and debug. So it was very interesting to actually get this working, debugging live inside of server-side JavaScript. It actually involves two processes. The debug is actually opening up a blocking socket connection to the debugger, so that's how we implement the stopping. If that socket read blocks, then that's how the debug is waiting. So now when I click on the button, you'll see that my breakpoint fired over here, and just like any other IDE, I can go in and I see the JavaScript variable image, its type. I see all of the members on that JavaScript variable and what their values are. I can come in here and run code. I can run code in the context of the JS context that's currently executing right now if I want to change something. So this is pretty powerful. And of course, if I continue, boom, it's going to blow up. This system in production, if I ran that app and it did that in production and it crashed, it kicks into the whole notification system we have so that the programmers that publish this automatically get notification, walkbacks, JavaScript and in native code of where the application failed. It automatically puts tickets into our bug tracking system, things like that. So it's a very self-healing system. Now, once this is available, we have other tools. How do you look at the performance of your app? So here, this is very in-depth information about our backend for running this JavaScript application. It took 14.46 milliseconds of CPU time to run this. A bunch of different databases and things that were accessed. We have built-in timers and checks in here to figure out where the time is being spent. If we were talking to any services, things like that, we can look at the actual schemaed requests going out to the services and not just see the requests and how long they took, but dive into them and actually see the payloads of the requests, which is pretty interesting for people. In addition to that, memory debugging. So people need to know how their JavaScript usage, like how many objects they're creating, because these apps can be long-lived apps, so they need to know, am I keeping objects alive? Is everything being GC'd? Is there a bug in the native code of one of these objects that's causing the reference to stay around for it to leak? So this is running live right now, so if I go over here and kill this, this should update. It doesn't update right now, but anyway. The point is, you can come in, inspect everything. You can see, okay, we'll wrap it up. You can see code. This is saying, this indicates that it's from native code. I'm not running in something that's supported right now, but you actually get native code walkbacks, JavaScript walkbacks of where this stuff broke. So that's it. We run out of time. I mean, this is like a lot of stuff to try to cram into 20 minutes, but we kind of wanted to show everybody, we've been doing this for years. We have a lot of time and effort invested into this tool chain and making everybody productive in it. So we hope that some of these ideas can carry over into the Node.js world. And I look forward to seeing Node.js get a competitor, SpiderMonkey, because we use SpiderMonkey. We can't use V8 for a bunch of reasons, but SpiderMonkey hasn't been really entering into the server-side arena. It's going to be soon. They're fitting it with a V8 harness to get it into a Spider node, so we'll see what that brings up. Thanks, everybody.